So in this lesson, I'm going to be talking about buffers. Now, buffers are solutions that are going to contain a weak conjugate acid-base pair. So what that means is you have a weak acid and its weak conjugate base, or a weak base and its weak conjugate acid. So a couple of examples we've already seen of solutions that have these. For example, if you have acetic acid and in that solution you also have acetate ions, that would be an example of a buffer. Or, for example, if you have a weak base like NH3 and its weak conjugate acid like NH4+ or ammonium, that is a buffer. Now, the reason why buffers are extremely important is that they actually help to reduce any extreme change in pH that could occur if you add a strong acid or a strong base. And so your blood is actually a buffer. It contains these two, this acid and base pair, those weak acid and base pairs, in order to make sure that if for some reason strong acid were added to your blood or exposed to your system, that you wouldn't immediately die. So I'm going to show you mathematically how buffers work and why they are so important. Before I do that, though, I want to talk about how to actually make a buffer. So remember, a buffer is simply your weak acid and weak base. And what we say is that a buffer is ideal if you have equal amounts of those two, because ultimately then it'd be able to react equally with a strong acid or with a strong base. And so a solution can be a buffer if it doesn't have equal amounts of the weak acid and weak base, but we call it ideal if it does. So I'm going to explain how to make these ideal buffers. So the first obvious way to do it is to take a weak acid and its weak conjugate base and simply add equal amounts. So for example, if I took 0.2 molar of acetic acid and I added exactly 0.2 molar of sodium acetate, remember we don't care about the sodium in this salt. All we care about is the C2H3O2-, which is going to act as the weak base. It's the weak conjugate base of acetic acid. So I add equal amounts of them, and look at that, I've got a perfect buffer. Well, what if I don't have my conjugate base? Well, what you could do is you can add your weak acid and then half as much strong base, and that will give you an ideal buffer still, equal amounts of your weak acid and your weak base. So let me show you mathematically how that actually works out. So for example, I could take 0.2 molar of my acetic acid and I could add half as much strong base. In this case, I'm going to add 0.10 molar of NaOH. So what this would look like, I'd have my acetic acid and I'd react it with hydroxide, and that would produce, remember this is an acid reacting with a base, so acetic acid is going to give up its hydrogen ion and it's going to give it to hydroxide. So what's going to be produced is water and your acetate ion. I'm going to create my ice chart quickly. I got 2.2 molar of acetic acid, 0.1 molar of NaOH. No, we don't care about water, right? A big X for water, and then 0 for my acetate ion. So because I am reacting a strong base with a weak acid, notice my arrow is not a double arrow. This is going to go to completion since sodium hydroxide is a strong base. So the change, my X, I already know right now. It's going to be 0.1. So I'm going to have 0.10, 0.10, and then I'm going to add 0.10 to my acetate ion. So at equilibrium, or at the end, ultimately, technically it's equilibrium still, I would have 0.10 molar of my weak acid, no hydroxide, and 0.10 molar of its weak conjugate base. So there, since I've got equal amounts of my weak acid and my weak base, I know I have an ideal buffer. Now, something that should be, some alarm bells should be going off, or I guess signals or whatever, because that should look familiar. Specifically, notice if I have equal amounts of my weak acid and its weak conjugate base, notice I used half as much strong base as I would have needed to reach my equivalence point, which means I'm at my half equivalence point. So remember, pH equals your pKa at your half equivalence point. Well, your half equivalence point, another name for that, is an ideal buffer. Okay, so ultimately this concept we've already gone over, but we're just going to go into it in more detail to make sure you understand all the little details about it. All right, so that's the second way. So I could have added equal amounts of weak acid and base, or I can add a weak acid and half as much strong base, or, as you probably thought about, you could add weak base and half as much strong acid. So let me give you an example. Let's say, for example, I have 0.20 molar of NH3, right? I could add half as much strong acid, in this case hydrochloric acid, and that would give me a buffer. So let's see what that would look like. So I have NH3, and it's going to react with my strong acid, so plus H plus, and that's going to produce my weak conjugate acid, which is going to be ammonium. Okay, I'm going to ice it. Initial concentration of ammonia is 0.20, 0.10 for hydrogen ion, and 0 for my ammonium ion. My change, because it's a strong acid, it's going to go to completion, so minus 0.10, minus 0.10 plus 0.10. And so at the end, I'm going to have 0.10 of my ammonia. I'm going to have no strong acid, and I'm going to have 0.10 of my ammonium. So notice NH3 is my weak base, NH4 plus is its conjugate acid. I've got equal amounts, therefore I've got an ideal buffer right there. All right, so it doesn't matter which one you start with, an acid or a base. Ultimately, your goal is simply to have weak acid and weak base, and if you want it to be an ideal buffer, you want equal amounts of weak acid and weak base. Okay, so we talked about how to make a buffer. Now, how does it actually react? Why do we care? So remember, your buffer is going to contain a weak acid, so in this case, it just gives a generic HX, and its weak conjugate base, so X minus in this case. So if I were to take my buffer, let's say, for example, my blood, and I were to somehow expose it for some reason to a strong acid, well, what would happen? Well, notice I've got a weak acid and a weak base. So the weak acid's not going to do anything with the strong acid that has suddenly been added, but instead, X minus, the weak base, will. So if you look up above, it shows X minus plus H plus. That's because your strong acid is reacting with the weak base that was present in your buffer. And so that's going to produce HX, all right? And then you can create an ice chart and actually analyze it to figure out what the pH would be. Or, let's say, for example, a strong acid were to be added. So let's say, for example, sodium hydroxide or whatever it is. Well, in that case, since it's a strong base that's being added, then HX is going to react, my weak acid is going to react with the strong base, and it's going to form X minus and water. And again, you can then create an ice chart and actually solve it. So keep in mind, you have a buffer there because you want HX and X minus. You want HX, the weak acid there, just in case a strong base is added. You want X minus there just in case a strong acid is added, because HX is not going to help prevent any change in pH if you add a strong acid. It's useless. It's only useful if you add a strong base. So that's why you want equal amounts of your weak acid and weak base, or as close to it as possible. All right, so let's look at an example. So example A says a buffer is made by adding 0.300 moles of acetic acid and 0.200 moles of sodium acetate to enough water to make 1 liter of solution. So clearly this is not an ideal buffer, because if it were, I'd have equal amounts of the acid and its weak conjugate base. But it still will act as a buffer, all right? First, I'm asking you to determine the pH of the buffer, okay? So I'm going to quickly show you how to use ice charts to do this, but really, guys, since you have a weak acid and a weak base, please use Henderson-Hasselbalch no matter how much you claim you don't like to use their formula, all right? But I'll show you it regardless. I'll show you how you can do it 2 different ways to determine the pH. So let's say, for example, I want to start with acetic acid. So I want to show the dissociation of my weak acid. So I've got my weak acid. It's going to break apart into acetate ions and hydrogen ions. I'm going to ice this. I know my initial concentration because I'm going to do 0.300 moles divided by 1 liter, which is just 0.300 molar. I know my initial concentration of my acetate, right? Remember, NaC2H3O2, Na does not contribute at all, so you're just going to be looking at C2H3O2 minus, okay? So the concentration of that is 0.200 molar, and I have no hydrogen ions yet, okay? This is a weak acid dissociation, so yes, my change is going to be minus X plus X plus X, so at equilibrium, 0.30 minus X, 0.20 plus X, and X, okay? So to solve for X and therefore get my pH, I'm going to have to write out my equilibrium expression for this acid. So it's going to be 0.200 plus X times X all over 0.300 minus X, and that's going to be equal to my Ka, which is 1.8 times 10 to the negative 5th. Okay? So in order to solve this, I'm going to pray and note that, oh my goodness, I can use my rule of 100, so I'm going to get rid of my plus X and minus X, and then I'm going to solve for X, and I got 2.7 times 10 to the negative 5th. take the negative log of that because that represents your concentration of hydrogen ions, and I get 4.57 for my pH. That's one way to do it. Awesome, fair enough. What if instead I didn't think about doing an acid dissociation? What if I just saw NaC2H3O2 and I was like, that's a weak base? Well, don't worry, I can do that as well and get the same answer. So I've got my weak base, C2H3O2 minus. It's going to react with water for a base dissociation. It's going to produce acetic acid and hydroxide. Okay, I'm going to ice this. I know my initial concentration of my base is 0.200. I have my initial concentration of acetic acid, 0.300. My initial concentration of hydroxide is 0 minus X plus X plus X. Okay. At equilibrium, my concentration of acetate ion is 0.200 minus X. For acetic acid, 0.300 plus X, and then X. All right. To solve for my X, keep in mind that this is a base dissociation reaction. So it's going to be 0.300 plus X times X over 0.200 minus X, but instead of a Ka value, which was 1.8 times 10 to the negative 5th, remember I need to take 10 to the negative 14th and divide by my Ka in order to get my Kb. So I got 5.6 times 10 to the negative 10th. Again, I can use my rule of 100, get rid of those X's, solve, and the X I get is 3.7 times 10 to the negative 10th. So when I take the negative log of that, my pOH is going to be 9.43, which means my pH, look at that, is 4.57 as well. So it doesn't matter if you do an acid-base dissociation. And not only that, you don't have to waste your time doing an acid-base dissociation reaction because you can just use Henderson-Hasselbalch. Don't hate on him, enjoy it. So pH equals my pKa, which is the negative log of my Ka, plus the log of my base concentration, which would be 0.200, divided by my acid concentration, which would be 0.300. And guess what pH I get? 4.57. So my recommendation, if you see that you have a weak acid and a weak base, make your life easy and use Henderson-Hasselbalch. They created a lovely formula for you to use. If you are stubborn and want to use an ice chart, fine, but be very careful and make sure that you don't make any silly mistakes. Okay? So I've just now taken my buffer and I found its pH. Now let's actually look at how it reacts with strong acids and strong bases. So for B, I'm going to take my buffer and now I'm going to add 0.020 moles of HCl to it. So the first thing I have to do is I have to see what exactly is formed in this reaction. Okay, so HCl is a strong acid, which means it is going to react with the weak base in my buffer, which is C2H3O2 minus. So that will react, my weak base will react with the strong acid H+, and it will form acetic acid. Now notice that the arrow is a single arrow simply because this is going to go to completion because you have a strong acid. So my initial concentration of C2H3O2 minus is the same, the 0.200. My initial concentration of H plus is now going to be 0.020 because you divided by 1 liter. And be careful, my initial concentration of acetic acid is 0.300 because those were my initial concentrations in my buffer. So my change is going to be 0.020, okay, and I'm going to add to the product side. I know it's subtracting simply because my strong acid is going to react with my weak base. And so what I get at my end is 0.1800 and 0.320. Now, if you wanted to take those concentrations of your weak base and your weak acid, and you wanted to write out either an acid dissociation or a base dissociation, solve for your X, figure out your pH, go for it. I will never do that because I like Henderson-Hasselbalch. So I'm going to use that in order to determine the pH. Okay? I know my Ka, it's the same 1.8 times 10 to the negative 5th. My base in this case is my acetate ion, so the concentration is 0.180, and my concentration of my weak acid is 0.320. So when I solve this, I get a pH of 4.49, which makes sense because since I added an acid, the pH should drop. But notice the pH didn't drop that much. It's still in the 4s, which begs the question, okay, well, what if instead of adding the HCl to my buffer, what if I just added it to water? How would that affect the pH? Well, if you just add a strong acid to water, I'm going to create my ice chart. You don't have to because technically it completely dissociates, so you know your concentration of H+ at your end, but I'm still going to show it. I have that concentration of my strong acid, no concentration of my ions. The change, because it's a strong acid, is going to be the entire amount, 0.020, plus, and so what I get at the end is a concentration of 0.020 of hydrogen ions. So since I've got just hydrogen ions there, remember Cl- doesn't affect the pH, I'm going to take the negative log of that value, and that gives me my pH. So unlike in the 4's value you just got when I added HCl to a buffer, if I just added HCl to my solution point blank, it would drop the pH from 7 all the way down to 1.70, which is a pretty significant change. All right, so that shows you the value of buffers. All right, so I've added a strong acid to a buffer and it's reacted with the weak base. What if I take a strong base and I add it to the buffer? Let's look at an example. So now instead of adding 0.020 moles of HCl, I'm going to add 0.020 moles of NaOH. So my strong base will react with the weak acid in my buffer, which in this case is my acetic acid. It'll react with hydroxide to form my acetate ion and water. So I'm going to ice this. I know my initial concentration of my acetic acid. I know my initial concentration of my sodium hydroxide. I know my initial concentration of my acetate ion, and I ignore water. So the change now is going to be minus 0.020, and I'm going to add 0.020 on my product side. So at my endpoint, equivalence point, whatever you want to call it, not endpoint, that'd be a bad name, just at your end, my concentrations are 0.280 of my acetic acid. I have no strong base, and I have 0.200 molar of my acetate ion. So again, weak acid, weak base, I like Henderson-Hasselbalch. My base, in this case, the concentration is 0.220, while my acid concentration is 0.280. And so the pH I get is 4.64. Okay, so the pH went up a little bit, which is expected because you're adding a strong base. Now, keep in mind, there's only a certain limit to your buffer. So for example, if instead of adding 0.020 of my base, what if I added 0.40 of my strong base? Okay, so instead of 0.02, 0.4. Well, in that case, yeah, the weak acid would run out, the pH would shoot up because I'd have extra of my hydroxide ion. Okay, so there's only a certain limit to how effective a buffer is. If you add too much acid if you add too much strong base or strong acid, yeah, at a certain point your buffer will run out and then it's no longer functional. However, for problems that we'll be doing, normally it doesn't run out. Normally it works perfectly fine. So that was adding a strong base to a buffer. Well, what if I just added a strong base to water? How would that change the pH? Would it be significant? Well, the answer is obviously yes. There's my base dissociation reaction there. I have 0.020 of my strong base, none of my ions yet. My change is going to be complete because it's a strong base. And so what I get is 0.020 molar of my hydroxide ion. To find the pH, I first have to find the pOH, which is 1.70, which means the pH is 12.30, which is very different than the value that I just got when I added the strong base to a buffer. So clearly, buffers are very useful. We need them in order to prevent a strong acid or strong base from coming in and completely changing the pH, right? And so, yeah, we use it in chemistry class. We use it for pharmaceuticals, but the most important thing for you is your blood is a buffer. And now you actually understand mathematically how that works. The fact that if a strong base is added to your blood for some reason, then the weak acid in the buffer will react with it. If a strong acid is added, then the weak base in the buffer will react with it. And that's it. So I was told I cut off my video, so I'm just gonna chill for a minute or two and not cut off my video, but if you want to cut me off, that's fine. But